Welcome to the deep dive. Get ready to unpack a topic that's, well, it's woven into pretty much everything we do these days.
It really is.
Whether you're scrolling on your phone, working on a computer, even stuff in your car or at the movies.
Everywhere.
Exactly. We're talking about the fundamental concepts behind computers and all the digital tech that powers, well, just about everything.
hmm
Now, you've shared a stack of sources, really comprehensive stuff, looking at how this all works, from the actual physical bits you can touch
Hardware, yeah.
to the invisible instructions making it run and how it all connects.
It covers a lot of ground.
So our mission for this deep dive is to kind of cut through all that information and pull out the real essential nuggets.
Get to the core ideas.
Yeah, give you a clear picture of how this digital world is actually built, understand the basic building blocks, and, maybe spark a few aha moments.
Sounds good. These sources really do lay out those foundational pieces well. They show how these incredibly complex systems are, at their heart, built from pretty understandable basic elements.
Okay, let's dive in then. The absolute basics. Right at the start, the source material breaks down any computer system into four fundamental bits: hardware, software, data, and users.
Right. And that last one, users. That's you, interacting with it all.
Okay, so explain that a bit more.
Think of it maybe like layers. Hardware is the physical stuff, circuits, chips, screens, keyboards,
The tangible bits.
Exactly. Software, then, is the set of instructions, the code, that tells the hardware what to do.
Okay.
Data is the information, the raw facts and figures that the software works with, that it processes.
Right.
And users, well, that's us. Giving input, needing output. It all operates on that simple input, process, output model. That's
So that input process output concept, it really feels like the cornerstone, doesn't it?
It absolutely is. You feed information in, the system crunches it based on the software's instructions, and that gives you results back out.
Simple idea, but it scales up massively.
Totally. That fundamental loop is key. Whether you're, I don't know, doing sums in a spreadsheet or rendering amazing graphics in a game, it applies from a tiny calculator all the way to a supercomputer. Still that core idea.
All right, let's metaphorically open up the box then. Look at the hardware essentials the sources get into. Right at the heart, the central processing unit, the CPU.
The brain.
We often call it the brain, yeah. But the sources give a bit more detail on what that actually involves.
Yes, it's the main workhorse, you could say. The CPU executes the instructions from the software and supervises the other parts of the computer.
Okay.
And inside the CPU, the sources mention things like the arithmetic logic unit, or ALU,
ALU, right.
which handles, the calculations and comparisons, and the control unit, which directs the flow of instructions and data.
And the sources also point out these things called registers that the CPU uses. Why are they important?
Registers. They're super important because they're the fastest possible memory for the CPU. They're actually located right inside the CPU chip itself.
Wow, okay.
They're tiny storage areas, but they hold the data and instructions the CPU is actively working on, like right this second. That speed is critical for processing things quickly.
Okay, so CPU does the work, registers are for the immediate stuff, but computers need way more memory than just those tiny registers.
Oh, absolutely.
The sources talk about a memory hierarchy. Sounds interesting.
Yeah, it's a really neat concept. It's all about balancing speed, cost, and how much you can store. Closest to the CPU, even faster than the main memory, you've got cache memory.
Cache. Heard of that.
Right. It stores frequently used data and instructions. The idea is the CPU can grab stuff from the cache much faster than going all the way to the main memory, the RAM.
So it's like keeping your most used tools right there on your workbench instead of having to walk to the toolbox every time.
Exactly. That's a perfect analogy. Then below cache, you have primary memory. This is mainly RAM, random access memory.
RAM. Everyone talks about needing more RAM.
Yeah. It's the computer's main temporary workspace. It's volatile, which is key, means it only holds data while the computer has power. Turn it off, RAM is wiped.
Right.
When you run a program or open a file, it gets loaded into RAM for the CPU to work on it quickly.
So that's the active workspace.
Right.
What else is primary memory?
Primary memory also includes ROM, read-only memory. Unlike RAM, ROM is non-volatile. It keeps its information even when the power's off. It stores really essential permanent instructions.
Light.
Like the Bootstrap loader. That's the little program that runs first when you turn your computer on, tells it how to wake up and load the main operating system.
Ah, so ROM gets things started, RAM is where the work happens now. What about saving my files, keeping stuff long term?
That's where secondary memory comes in. This is your non-volatile storage, things like hard drives, SSDs, USB drives. It's where your data and programs are kept permanently, or at least until you delete them. And the trade-off across this whole hierarchy is pretty clear, as the sources point out. The faster the memory, like cache and RAM, the more expensive it usually is per unit of storage, and you generally get less of it compared to the slower, cheaper, but much larger secondary storage.
Speed costs money, basically.
And capacity. You pay for speed.
Now, the sources also mention something about how the design of the storage affects access speed, contrasting sequential and direct access.
Yeah, this is a great point about how the physical technology matters. Sequential access. Think of old magnetic tapes like the source mentions.
Like an old cassette tape.
Exactly. To find a specific song or piece of data, you have to physically wind through everything in order from the beginning. You can't just jump there.
Okay. Tedious.
Very. Direct access, on the other hand, which is what hard disks and SSDs use, lets the system jump almost instantly to the specific physical location where the data is stored.
Like picking a track on a CD or digital file.
Precisely. That ability to randomly access any piece of data quickly is, well, fundamental to how fast modern computers feel. Huge difference.
Makes total sense. Okay, processing, memory, covered. How do we talk to the machine? Input and output devices. That's the bridge.
That's the bridge. And the sources give examples we all use constantly. Input, you've got the keyboard for typing text, the mouse, which it describes as a pointing device for point, click, drag actions.
Things we do without even thinking.
Right. Second nature. But they also mention more, maybe specialized input methods, like biometrics.
Oh, yeah.
Fingerprint scanners, for instance, used for identification, authentication. You're inputting your physical characteristics.
Okay. And output. Getting stuff back out.
Displays are the big one. Monitors. The source points out that clarity depends on things like resolution, how many pixels, dot pitch, how close the pixels are, and refresh rate, how often the image updates.
Right. Things you see listed when buying a monitor.
Exactly. And printers, of course, for physical output. Hard copies.
The sources mention impact versus non-impact printers. Is that still relevant?
Well, it describes the mechanism. Impact printers, like old dot matrix ones, physically strike an inked ribbon against the paper.
Newsy.
Yeah, often. Non-impact printers, like inkjet or laser printers, use other methods spraying ink, or using toner and heat. The difference mostly affects speed, noise, and sometimes quality. Printer quality is often measured in dpi, dots per inch.
Higher dpi means sharper printouts.
Generally, yes. More dots packed into the same space.
Okay, got the physical machine sorted. But hardware, as you said, is just potential. It needs instructions. Software.
Exactly. Software gives the hardware purpose. It tells it how to perform tasks. And the sources make a key point. The same hardware can do totally different things just by loading different software.
That flexibility is amazing.
It is. Software generally falls into two big categories: system software and application software.
Okay, what's the difference?
System software provides the basic operating environment. It manages the hardware resources.
Yeah.
The most important piece here is the operating system, or OS.
Like Windows or Mac OS or Linux?
Precisely. The
Oh.
OS is like the manager, the intermediary between you, your applications, and the raw hardware. It's crucial.
What does it actually do? The sources list a bunch of functions.
Yeah, it juggles a lot. It manages processes. That's all the programs that are running. It manages memory, deciding which program gets how much RAM. It manages files, organizing data on your hard drive. It controls devices, talking to your printer, your webcam. It provides security features. And importantly, it provides the user interface.
The way we interact with it.
Right, often a graphical user interface, a GUI. That's your windows, icons, menus, pointer, the visual stuff you click on.
The GUI is what most of us think of as the computer, really.
Pretty much, yeah. It's our window into the system.
Now, the sources also mention programming languages and translators. This is interesting. Why can't computers just understand English or any human language?
Fundamentally, computers only understand one language: machine code.
Binary. Zeros and ones.
Exactly, just sequences of zeros and ones. That's all the hardware gets. But writing that directly is incredibly difficult for humans.
Yeah.
So we use high-level languages like Python, Java, C++, which are closer to human language.
Okay.
But the computer can't understand those directly. They need to be translated into machine code. And the sources describe the two main ways that happens: using a compiler or an interpreter.
Compiler versus interpreter, what's the difference there?
A compiler takes your entire program, all the source code written in a high-level language, and translates it all at once into machine code, creating a separate file, usually called an executable. You run that executable later.
Okay, translate everything
Yeah,
first.
right. An interpreter, on the other hand, works differently. It takes the program one line or one statement at a time. It translates that line, executes it, then moves to the next line, translates it, executes it, and so on.
Line by line.
Line by line. This difference matters. Compiled programs generally run faster after they're compiled because the translation is already done. Interpreted programs can be a bit more flexible during development, as you can run them immediately without that separate compilation step.
That's a really clear distinction, performance versus flexibility, in a way.
Often, yeah. It's a classic trade-off in computing.
So how does all this software actually get to us, the users? The sources list different ways it's made available.
Right, there are various models. You've got retail software, the traditional buy-in-a-box or download-after-purchase kinds.
Standard stuff.
Then there's shareware. That's often like try before you buy. You might get a free trial period or limited features.
Okay.
Freeware is software that's completely free to use, no charge, though the author usually retains copyright. Public domain software goes even further. There are no copyright restrictions at all. Anyone can do anything with it. And then there's open source software. This is a big one. The source code itself is made available. It's often free, but comes with licenses that specify how you can use, modify, and redistribute the code. Think Linux or Firefox.
So lots of different ways software comes into the world.
Definitely affects how accessible it is and how it gets developed.
Okay, moving outwards now. Computers today rarely work alone, do they? They connect. Networks.
Absolutely essential today. The sources define a network quite simply. An interconnection of two or more computers that are able to exchange information. That exchange is the key.
Sharing data, resources.
Exactly. That's the power. The sources categorize networks mainly by size, by scale. You have a local area network, a LAN.
LAN party.
Oh, yeah. Connects computers in a limited area, like one office building, maybe a home network.
Yeah.
Then you have wide area networks, WANs. These cover much larger areas, cities, countries, even globally. Think of the internet itself, or cellular data networks. Those are WANs.
Okay, LANs are local, WANs are wide. How does the information actually zip across these networks? What carries the signal? The sources talk about the physical media.
Good question. They highlight two main types. First, copper wires. Things like twisted pair cables, like your typical Ethernet cable, or coaxial cables, like older TV cables. These use electrical signals.
Okay.
They work well, but the signal strength can drop off over longer distances. They're susceptible to interference sometimes.
And the alternative?
Optical fiber, fiber optic cables. These transmit data as pulses of light down thin strands of glass or plastic.
Light signals. Sounds fast.
Very fast. Fiber allows for much higher bandwidth, carrying more data at once, and the signal travels much further with less loss. That's why it's used for like the main backbones of the internet and long-distance connections. Totally different technology, much higher performance.
Makes sense why fiber is such a big deal. And all these networks connecting together. That brings us to the biggest one, the internet.
The network of networks. The sources mention its history, starting way back with ARPANET, a U.S. defense project.
Right.
But it grew into this huge decentralized network we use constantly today. It's not owned by any single entity.
How do computers find each other on this massive thing?
Every device connected to the internet needs a unique address, like a phone number. This is its IP address, Internet Protocol address. It's a series of numbers.
Like 192.168.1.1, that kind of thing?
Exactly like that. But numbers are hard for us humans to remember. So we use domain names like, say, google.com or deepdive.com.
Much easier.
Way easier. And the domain name system, DNS, acts like the internet's phone book. It translates those human-friendly domain names into the numerical IP addresses that computers actually use to locate each other.
Ah, so DNS is the translator.
It's the essential directory service. And when you see a full web address, like https://www.deepdive.com, episode 1, that's a uniform resource locator, or URL, it specifies the protocol, HTTPS, the domain name, and the specific resource or page you want on that server.
Got it. So what are the key things the internet actually lets us do, according to the sources, the main services?
Well, they highlight the big ones we all use. The World Wide Web, that collection of interconnected documents and resources we access using web browsers.
Chrome, Firefox, Safari.
Yep. Yeah, we find things on the web using search engines like Google or DuckDuckGo. Then there's electronic mail, email, sending messages instantly across the globe.
Can't live without it.
Pretty much. And file transfer protocol, FTP. That's a way to transfer files directly between computers over the network. Still used quite a bit, especially for web development and larger file transfers. These are just a few core services built on that network infrastructure.
Okay, so we have processing, connections, services, all generating and using massive amounts of data, which leads to databases. The sources explain why we needed them, talking about issues with older file systems.
Yeah, before modern databases became common, data for different applications was often stored in separate, isolated files. And this caused problems, as the sources point out.
Like what?
Big ones were data inconsistency. You might have the same customer's address stored differently in two different files. And data redundancy, storing that same address multiple times, wasting space and making updates a nightmare. Plus, it was often really hard to access or combine information that was spread across different unrelated files.
Sounds messy.
It was very inefficient. The database approach was developed to solve these problems.
And the benefits were?
Pretty significant. The sources list key advantages. Data sharing, multiple users and applications can access the same central pool of data. Reduced redundancy and inconsistency, you store data ideally only once, making it more accurate. Data independence, this is important. You can change the underlying structure of the database without necessarily having to rewrite all the applications that use it, and often reduced application development time because managing the data is handled more centrally.
So much more organized and efficient.
Definitely. A big step forward for managing information.
The sources mention the relational model being very common today for databases. What are the key terms we should know there?
The relational model is conceptually quite simple, which is part of its power. It organizes data into tables. Think of a spreadsheet.
Okay, rows and columns.
Exactly. A table is made of rows and columns. Each row represents a single record or entity, like one customer, one product. Each column represents an attribute or property of that record, like name, email address, price.
Simple enough.
And the crucial part is the key, often a primary key. This is a specific column, or maybe a combination of columns, whose value uniquely identifies each row in the table, like a unique customer ID number. You need that unique identifier to link tables together and manage the data accurately.
That unique ID is, well, key.
Couldn't resist, huh? But yes, it is absolutely fundamental to making the relational model work.
Okay. Now, with all this data flying around on networks being stored, security becomes hugely important. The sources introduce the basics: threats, vulnerabilities, attacks.
Yeah, essential security concepts.
Yeah.
A threat is any potential danger or source of harm to your system or data.
Potential harm.
Right. A vulnerability is a weakness. A flaw in the system's design, implementation, or configuration that a threat could exploit.
A weakness.
And an attack is the actual action taken by someone or something like malware to exploit a vulnerability and cause harm. Threat, vulnerability, attack. That's the sequence.
Got it. And a major type of threat is malicious software, malware. The sources list a few common types.
Yes, knowing the types helps. Viruses are pieces of code that attach themselves to legitimate files or programs. When you run that infected file, the virus activates and tries to spread to other files.
Like a biological virus.
Pretty much the analogy, yeah. Worms are a bit different. They are standalone programs that replicate themselves and spread across networks, often automatically, by exploiting vulnerabilities. They don't need to attach to another file.
They spread on their own. Sneaky.
Very. And Trojan horses are programs that pretend to be something useful or harmless,
Yeah.
maybe a game or a utility, but secretly contain malicious code that executes when you run the program. Named after the Greek myth, of course. Exactly. Viruses infect, worms spread, Trojans deceive. Different methods.
Hacking is another big area of concern mentioned. Things like denial of service attacks.
Right. A denial of service, or DOS attack, aims to make a computer or network resource unavailable to its intended users, usually by flooding it with so much traffic or so many requests that it gets overwhelmed and can't respond to legitimate requests.
Just flooding the gates.
Pretty much. The sources also mention password cracking. That's hackers trying to discover passwords, either by guessing, using common password lists, or using software to try millions of combinations systematically.
Scary stuff. So how do we protect ourselves? What are the security mechanisms the sources discuss?
Several key layers of defense. First, user identification and authentication. Basically proving who you are.
Passwords.
Passwords are the most common method, yes. But the sources rightly point out that weak passwords are a huge vulnerability. Stronger methods include biometrics using unique physical traits like fingerprints or facial recognition, also mentioned in the input section. Then there's cryptography. This involves encrypting or scrambling data using mathematical algorithms and keys so that even if someone intercepts it, they can't read it without the correct key. Essential for protecting data when it's stored or sent over a network.
Scrambling the message.
Exactly. And firewalls. Think of a firewall as a security guard or a barrier between your internal network or your computer and the outside internet. It inspects network traffic coming in and going out and blocks anything that doesn't meet the defined security rules.
The gatekeeper for network traffic.
A crucial gatekeeper. And importantly, the sources also mentioned that security isn't just about technology. User awareness, people understanding the risks and how to act safely online, and having a good organizational security policy, clear rules and procedures are just as vital. The human element is often the weakest link.
Good point. Technology alone isn't enough. Okay, wrapping up, the sources give us a glimpse of some common software tools that bring all these concepts together, like specific elements in operating systems, using Windows XP as an example.
Right. It shows how those OS functions we discussed earlier actually look and feel to the user. It talks about the Windows desktop, the main screen with icons, the taskbar at the bottom, the start menu.
A familiar interface for many.
Very. And it covers basic file management, creating, deleting, copying, moving files and folders, using the recycle bin. It even mentions specific system tools like ScanDisk, which was used to check hard drives for errors. These are the everyday ways you interact with the OS to manage the hardware and data.
And then there's application software, the programs we use to actually do specific things.
Exactly. Taking the OS foundation and building useful tools on top. The sources list common examples most people know. MS Word for word processing, creating text documents.
Yep.
MS Excel for spreadsheets, doing calculations, making charts, analyzing data. MS PowerPoint for creating presentations with slides. And MS Access for database management, letting users create and manage their own databases to organize information.
The classic Office suite tools.
Pretty much. And interestingly, they also mention LaTeX as an alternative document preparation system. It's different from Word, more code-based, but highlighted for producing really high-quality, especially technical or scientific, documents. Shows there are different tools for similar jobs built on the same underlying computer principles.
Wow. Okay, we've covered a huge amount of ground. From the tiny registers inside the CPU, out through memory, networks, the internet, databases, security, and finally specific applications. It really does feel like a lot of pieces fitting together.
And that's honestly the biggest takeaway, I think. While we talked about hardware, software, data, networks, security, applications kind of separately, the real insight is they absolutely don't exist in isolation.
They're all interconnected.
Deeply interconnected. They're layers of one integrated system. The hardware runs the software. The software processes the data. That data might be in databases, accessed over networks which need security, and is all presented through applications. Understanding these individual building blocks helps you see how the whole complex digital world actually functions.
And for you listening, this foundational knowledge, it really helps make sense of everyday things, doesn't it?
She should, yeah.
Why your phone needs software updates. Why some websites load faster than others, maybe network speed, maybe caching. Why choosing a strong password matters so much, authentication, vulnerabilities. Or even just how that spreadsheet instantly recalculates when you change a number. That's the input process output loop, the software, the data, all working together.
It's all built on these core principles described in the sources.
Well, that wraps up our deep dive into the fundamentals of computer systems, drawing from all that great source material you provided. We've definitely just skimmed the surface on some areas.
Oh, for sure. Each one could be its own deep dive.
True. But hopefully you now have a much clearer picture of the basic concepts, the building blocks that underpin the entire digital world around us.
Yeah, maybe next time you use your phone or browse the web, think about those layers, the hardware, the OS, the network, the application, all working together, hopefully seamlessly.
It really is amazing when you stop to think about it. And here's a final thought, something to chew on, that actually comes directly from the sources. They mention artificial intelligence, AI, as being the foundation for what they call the 5th generation of computers.
Okay, ahead.
So considering everything we've just unpacked, the hardware, the software, the data, the networks, the security, what does it really mean when sophisticated AI starts getting deeply integrated into each of those fundamental layers? How might AI reshape the very building blocks we've just explored?
That's a fascinating question. Big implications.
Definitely something to think about. Thanks so much for joining us for this deep dive. We really hope it gave you some valuable insights into how our digital world works.